Welcome to this explainer. Today, we're demystifying the mathematical framework of quantum computing. We're going to take a step-by-step journey starting from basic classical bits all the way up to complex multi-qubit circuits. If you've ever felt totally overwhelmed by the dense physics and math behind quantum mechanics, well, you're absolutely in the right place. We're keeping things clear, highly professional, and perfectly structured.
Okay, let's look at our roadmap. We'll cover 1. Bits versus quantum bits. 2. Linear algebra for quantum. 3. Visualizing the Bloch sphere. 4. Single qubit logic gates. And finally, 5. Multi-qubit systems and gates. Let's get to it.
All right, section 1, bits versus quantum bits.
So think about classical bits. They're definitive, right? They're easily copied. They are strictly either a 0 or a 1. Their information is super rigid. But quantum bits, or qubits, they play by entirely different rules. They actually exist in continuous linear combinations of 0 and 1. You can only measure them partially, and the very act of measuring them permanently changes their state. And get this, because of the fundamental laws of quantum mechanics, you literally cannot perfectly copy or erase a qubit without completely destroying the original information.
Which brings us to the famous concept of superposition. A qubit in superposition is essentially existing in both the off and on states at the exact same time. It's kind of like Schrödinger's cat in a black box. Because both a living and a dead cat are technically valid solutions to the laws of quantum mechanics, a superposition of both states is equally valid. Well, right up until the box is opened and measured.
And that actually illustrates what is probably the most counterintuitive part of quantum mechanics, the rules of measurement. See, while the underlying quantum system evolves smoothly and predictably, following linear equations like the Schrödinger equation, the measurement itself is this abrupt, sudden event. A quantum measurement is never going to hand you the full mathematical superposition equation to read. No way. You'll only ever see one state or the other, a definitive 0 or 1 based on a strict mathematical probability. Measuring the system literally forces that delicate superposition to immediately collapse into a single reality.
Moving right along, Section 2, Linear Algebra for Quantum. If you want the master key to quantum math, it's linear algebra. The state of a single qubit, which we denote with the Greek letter psi, is mathematically equal to alpha 0 times the 0 state plus alpha 1 times the 1 state. Now, the absolutely crucial point here is that alpha 0 and alpha 1 aren't your standard percentages. They're complex numbers called probability amplitudes. To figure out the actual probability of measuring a 0 or a 1 in the physical world, you have to take the absolute square of these complex numbers. And since the qubit must absolutely exist in some state, their absolute squares have to add up to exactly 1. We call this inescapable rule the normalization condition.
Now you might be wondering about those distinct brackets around the 0 and 1. That's bra-ket, or Dirac notation. It uses kets, like ket 0 and ket 1, to formally represent basis vectors for our quantum states. By using these vector representations, we can rigorously show how the absolute square of alpha 0 gives us the probability of an off state, and alpha 1 gives us the probability of an on state. It's a really powerful way to turn totally abstract, unobservable quantum states into rigorous, calculable column vectors.
All right, section 3, visualizing the Bloch sphere.
It's amazing how this vector equation perfectly maps onto a three-dimensional unit sphere, what we call the Bloch sphere. The north pole represents the pure state 0, and the south pole represents the pure state 1. Literally any point on the surface of this sphere represents a valid, normalized quantum state in superposition. The angles theta and phi, they directly correspond to those complex probability amplitudes we were just talking about. So this gives us a fantastic physical intuition for what a complex mathematical superposition actually looks like in geometric space.
Which brings us to section 4, single qubit logic gates.
So just like classical digital circuits use logic gates, quantum circuits use quantum dates to manipulate qubits. But they operate under some pretty strict mathematical constraints. Remember that normalization condition we mentioned, where the probabilities have to total 1? Well, because quantum systems are entirely based on probability preservation, every single operation has to be represented by a perfectly reversible and unitary matrix. If a logic gate is acting on just one single qubit, the underlying math uses a 2x2 matrix.
Let's see how these unitary matrix operators actually work in practice. Take the NOT gate, also known as the Pauli X gate. Its matrix acts just like a classical NOT gate by switching the 0 and 1 basis vectors. Multiply the Pauli X matrix by a ket 0 column vector, and boom, you get a ket 1 vector. Simple enough, right?
Then there's the poly-Z gate. This acts as a phase flip. It completely leaves the zero state alone, but you'll notice the poly-Z matrix has a -1 in the bottom right corner. That's because it multiplies the Ket1 state's probability amplitude by -1. Basically, it rotates the state 180 degrees around the z-axis of our Bloch sphere.
Now, let's look closely at the poly-Y gate. This one brilliantly illustrates why we absolutely need complex numbers in quantum computing. The poly-Y matrix uses positive and negative I, the imaginary unit, right inside its matrix operator to manipulate the qubit. When you apply this gate mathematically, it rotates the qubit's vector around the y-axis of the Bloch sphere, seamlessly intertwining those probability amplitudes with complex mathematical phases. It's really elegant.
And that brings us to the truly amazing Hadamard gate, usually just denoted by the letter H. This is an operation that has absolutely no classical equivalent. Seriously, zero. If you feed a definitive classical acting Ket0 state into a Hadamard matrix, it perfectly transforms it into an even 50-50 superposition of both 0 and 1. This single matrix operation is literally the foundational engine of quantum parallel computation. It's what allows us to evaluate massive, complex possibilities all simultaneously.
Finally, Section 5, Multi-Qubit Systems and Gates. Think about this for a second. To truly double the computational power of a standard classical digital computer, you have to upgrade your entire architecture, like moving from 32 to 64 bits. But to double a quantum computer's power, you merely jump from 32 to 33 qubits. Because a quantum computer operates on all superpositions at once, adding just one single qubit doubles the dimensionality of the mathematical space it can compute within. It's a mind-blowing kind of scaling.
Of course, handling multiple qubits means exponentially expanding our math. A single qubit uses a 2x2 matrix. But a 2-qubit gate, like the controlled NOT or CNOT gate, that requires a 4x4 dimensional matrix. The CNOT gate acts as a reversible analog to the classical XOR gate. It essentially flips the state of a target qubit if and only if the control qubit is in the 1 state. This specific gate is absolutely crucial for creating quantum entanglement, where the state of one qubit becomes inextricably linked to another, creating these highly correlated non-independent states. That's a stark contrast to non-entangled or separable states, where the mathematical state of one qubit can be completely described independently of the other.
When qubits are part of a multi-state entangled system, our linear algebra scales up beautifully. Take a typical state equation for a 2-qubit system. It's a vast superposition of 4 possible states, 0, 0, 0, 1, 1, 0, and 1, 1, and each has its own probability amplitude. We can rigorously calculate partial measurements, like finding the exact probability of reading just the rightmost bit as a 0, simply by summing the squared amplitudes of the relevant states. So here we square 0.316 and add it to the square of 0.548. That yields exactly 0.4, or a 40% probability. The math remains perfectly, wonderfully consistent as it scales.
And all of this comes together flawlessly in the quantum circuit model. We have fixed-width horizontal wires that represent individual qubits, and time mathematically flows from left to right. We link a sequence of single-qubit gates, like the Hadamard, to create vast superpositions, with multi-qubit gates, like the CNOT, to create intricate entanglement. And then we end finally with measurement operators that collapse all that beautiful math into readable data. This architecture is what allows us to perform massively parallel computations on superpositions, doing in one mathematical sweep what might take a classical supercomputer thousands and thousands of operations.
So we've journeyed all the way from the linear algebra of a single probability amplitude to the massive unitary matrices of highly entangled circuits. And it leaves us with a pretty incredible question. As we master this mathematical language and successfully build larger, stable quantum circuits, what massive, previously unsolvable problems in chemistry, medicine, and cryptography will we mathematically conquer next? Thank you so much for exploring the math with me in this explainer today.